Hello everyone, welcome to my talk. Today I will talk about a nearly linear time algorithm for linear programs with small treewidth, a multi-scale representation of robust central path. This is a joint work with Celadon and IntelliLi. So the linear program we want to analyze here has the following form. We want to minimize the inner product between the cost vector C and the solution vector X, where the solution vector X is supposed to satisfy the linear constraint, Ax equals to B. And each coordinate of X lies inside some interval Li to Ri. In this paper, we are interested in the scheme that the treewidth of constraint matrix A is bounded by tau. We will explain what the treewidth of a matrix means in a second, so now just bear with me. We also extend our result to the following convex generalization. Here, solution X is a concatenation of vector xi's, which we call them blocks. And each block xi has dimension ni, which we assume to be constant. And here, instead of letting each coordinate of X lies inside some interval, we require each block of X lies inside some convex set Ki. Now we can see why it's a treewidth. Informally, we see a graph has treewidth bounded by tau. If for any subgraph edge of graph G, the subgraph edge has a band separator of size at most tau. Here are some examples. For any tree, the treewidth of that tree is 1, and for any complete graph Kn, the treewidth is n. And Lifton and Tarjan shows in 1970s that any planar graph have treewidth at most square root n. And intuitively, for any subgraph edge of G, the treewidth of subgraph is more than the treewidth of original graph. And why is the treewidth of a matrix? Here, given a matrix A, we construct the corresponding dual graph GA by adding an edge UV to the graph if there is a column C such that both AUC and AVC are non-zero. The alternative definition is the adjacency matrix of GA is defined by the non-zero pattern of AA transpose. And the treewidth of the matrix A is defined to be the treewidth of the corresponding dual graph GA. Here, the first definition shows that if a column has k many non-zeros, then it implies there is a clique of size k in its dual graph. So if a variable appears in k different constraints in the constraint matrix, then the matrix at least have treewidth at least k. And it also shows that the number of non-zero of matrix A is bounded by n times the treewidth. Okay, now we need some related works. Historically, the problem of solving linear program is very well studied, and we all know how to solve linear program in time n to the omega, where n to the omega is the time it takes to multiply an n by n matrix. And recently, by Michael Cohen, IntelliLi, and Zhao Song, they show that they can solve general linear program in time n to the omega. And later, Yan Van Den Brand, IntelliLi, Aaron Thedford, and Zhao Song show that for tall dense linear program, they can solve it in nd plus d cubed time. And here, the tilde hides the polylog n over epsilon factors. And for the result related to the treewidth, in last 90s, there is Alan George, Joseph Liu, and Esmond N show that they can solve linear system in time n tau square. And recently, by Foreman et al., they show there is a series of problems can be solved in near linear time if the treewidth is small. For example, the unweighted max matching and the max vertex flow, which can be solved in n times tau cube and n tau square time. And in their paper, they conjecture that for the linear program, it can be solved in n times poly tau time. even though their notion of Treewidth for the linear program is slightly different with ours. And in the next slide, we will explain why we think our notion of Treewidth is a natural one. In our work, we show that we can solve both linear program and the convex generalization in O tilde n times tau square time. And we know that this runtime is optimal without using the fast matrix multiplication. That is when omega is to 3, because the running time matches the time it takes to solve a linear system in the dense case. Okay, now we list some application of our work. The most directly application is the flow problems. For basically the entire class of flow problems, the matrix Treewidth definition matches the definition of graph Treewidth. And here, one example is mean cost flow, where we want to solve the following linear program problems. And here the constraint matrix is B, which is the incidence matrix of graph G. And we know that BB transpose is exactly the Laplacian matrix of graph G. And it has the same non-zero pattern as the adjacency matrix. This shows the Treewidth of B is exactly the Treewidth of G. So for a series of flow problems, we can solve it in near linear time if the graph has small Treewidth. The second interesting application is signal denoising. Given an input signal U, we want to minimize the following function. Here, the first term restricts the output signal to be close to the input signal, and the second term controls irregularity of the output signal. How can we reduce this problem to our convex generalization? Turns out, for a general class of problem looks like this, where we want to minimize a sum of convex functions, where each convex function only depends on a small set of coordinates of our input vector. We can rewrite this problem in the following format. Here, by creating the copy yi for each set of xsi, we can show that here the convex constraint, this set is exactly a convex set because phi I is a convex function. And because for the signal denoising problem, each variable is only copied constant many times, this implies the constraint matrix here has constant Treewidth, and it directly gives us a nearly linear time algorithm. The third application is what we call one-dimensional convex regression. We are given a set of data points, x1, y1 to xn, yn, and we want to find a discrete convex function f that minimizes the LP norm of f minus y. Here, since f is a discrete convex function, so we define the local slope and local curvature in the following way. And we know that we can rewrite this convex constraint and the following linear constraint. And since each variable fi only intersects with constant many other variables, it again implies that the constraint matrix has constant Treewidth and results a near linear time algorithm. Now we can explain how does our algorithm works. For the simplicity of this talk, we will only explain how to solve linear programs in n times polytotal time. Okay, the standard way to solve linear program is using what we call central path method, where it reduces solving linear program into solving square root of many different linear systems. And the standard central path method can be expressed as the following, where for each iteration, we update x by the following formula, and we update it for the square root n many times. Here, D is a diagonal matrix, and Dii and Hi only depends on Xi. In our paper, we use a variant of the standard central path method, what we call robust central path method. The main difference is instead of updating x using exactly formula of solution vector x, we allow it using some L infinity approximation of X. We call it X bar. And in the paper, we show that using lazy updates on X bar, the total number of coordinate change is at most linear. Okay. So we know that since the matrix A is very sparse, we can compute the right-hand side AD inverse H very efficiently. And the bottleneck is only solving the following linear system. The standard way to solve this linear system is what we call the inverse maintenance, where we write down M equal to AD inverse A transpose, and we compute this inverse explicitly and maintain it. Whenever we need to compute this linear system, we directly compute it by multiply M inverse with the vector U. However, this approach cannot work here because both M inverse and M's update can be totally dense, and this will result at least a square runtime. But here we are opting for near linear time. Okay, so the way we avoid this problem is using what we call sparse Cholesky decomposition to maintain that M implicitly. So each positive definite matrix can be unique factor as product of L transpose. Well, here L is a lower triangular matrix. And when A has more choices, then this decomposition have some nice properties. The first one is we can find this decomposition in n tau square time. And each column of L has column sparsity tau. And for the linear system, we can solve the lower triangular system in input sparsity times tau square time. Now our goal is to maintain this AD inverse A transpose by L transpose. And it turns out for coordinate change in diagonal matrix D, it only takes tau square time to update L. And hence, we can maintain L in time n times poly tau. And this also implies the total number of coordinate change of L is at most n times poly tau. Okay, recall, our goal is to compute this linear system using the Cholesky decomposition. And we know that it's very easy to compute L inverse U. We can directly maintain the update using the following formula. However, compute L inverse transpose is still very hard because L inverse transpose can be dense even if V is very sparse. Our solution to this problem is implicit representation with sketching techniques. So we maintain the solution vector X in the following form. We call this form and multiscale representation. And we call the red part and multiscale coefficients. We know that for any coordinate I, we can compute xi in poly tau time because even though L inverse transpose is very hard to deal with, when we are only interested in a single coordinate of x, we can take the transpose. So here, the L inverse AD inverse EI is very easy to compute, and hence we can compute xi in poly tau time. And the second property is this is very easy to maintain after update to the x. So when D changes, we can directly compute the corresponding entry of xi and move the arrow to the x0. And the change of U is very easy because you can directly move the arrow to the U. For the change on the L, we know that we can update U using the following formula. Hence, we can maintain this representation after the change to the x in the poly tau time. And we further know that whenever we need to update x to the next iteration, we can simply move the counter a to a+1. Hence, the total number of coordinate change of scale coefficient is n times poly tau, and we can maintain this multiscale representation in n times poly tau time. Okay. So we have this implicit representation of our solution vector x, but we still need to L infinity approximation x bar in order to run the central path method. So how do we do that? Our solution is using some sketching techniques. We show that we can actually construct a data structure that support the following operation. One is we can update the corresponding L infinity approximation. And the second one is it supports output a random coordinate of x with probability proportional to its L2 norm. Once we get this data structure, we already solve our problem, because once we have a L2 norm squared sampler, then we can directly convert it to the L infinity sampler. Then we can maintain the L infinity approximation using linear number of sample calls. Okay, then now we go through our final part of our work, which is constructing the sampling data structure. One of the most important ingredients of the data structure implementation is what we call sampling tree. Here, the sampling tree is any arbitrary tree with constant degree and a labeling on the vertices, where each node on this sampling tree corresponding a subset of indices of solution vector, and each leaf in this tree is correspond to exactly one coordinate of the solution vector. And once we have the sampling tree, we can maintain a sketch by multiplying a sketching matrix on the left for each node in the tree. And using the sketch, we can estimate the L2 norm square of those subset of indices. And we do a random descent based on those estimation. Because here we multiply a sketch matrix on the left, we do a reject sampling to avoid the adaptivity issue. In the paper, we give two different constructions of the sampling tree. One is what we call the simple sampling tree. This is directly based on the elimination tree, and you will see in the next slide. And there is another sampling tree, what we call the balanced sampling tree. This is a much more complicated construction, where we are using a binary tree to maintain the depth first search order of the elimination tree and ensure the height of that sampling tree is at most norgan to achieve the n-tau square running time. Okay, so what is the elimination tree? The elimination tree is the data structure we use to keep track of non-zero pattern of lower triangular matrix L. Here we give a very concrete example. So we can see that for any column of lower triangular L, the non-zero pattern corresponds to exactly a subset of the path from corresponding vertex to the root. For example, here, the column 8 has non-zero at 8, 9, 10. And we work from 8 to the root 10. So it's exactly 8, 9, 10. And for another example, 6 have the non-zero pattern, 6, 7, and 9. So here you can work out to the path is 6, 7, 9, 10. So it's exactly a subset of that path. And for the simple sampling construction, again, we use a matrix and we get the corresponding elimination tree. And since here each node here is corresponding to a column in the matrix, and we want the sampling tree, each leaf corresponds to a row in the matrix. So we are adding some leaves under each node to construct the simple sampling tree. But you can see the structure is totally preserved in the sampling tree. Okay. Now, finally, how do we maintain the sketch on the tree? So for each node in the sampling tree, we actually need to maintain two parts. One part is the sum of the path from the vertices to the root, and another is the sum of the whole subtree. And know that whenever we do an update on L, actually the value on whole path changes. That means the sum, every sketch on the whole tree is changed. We avoid this problem again by only maintaining the subtree sum and compute A on the fly, because the height of tree is at most tau. And that ends our talk. Thank you for listening.